All right, here we go. Physics reaction video number 23. And today I did a search for AP Physics HW. And this is what I got. Just reading it quickly. Seems like we're in kinematics, I guess. Yeah, okay, so let's get started.
All right, hi everybody. So the three questions that were most requested were numbers 9, numbers 11, and...
Ooh. That was cool. The three numbers that were most requested. So this is an approach that that I find really, really intriguing, and I certainly have done it a lot. Where when I first started doing flipped physics, flipped teaching, I guess, I would look at the book and I'd say, "Ooh, that's going to be confusing. I better make a video about that." And I switched to the backflip, what I call a backflip, where we go into class, we engage with materials, we try to really sort of figure out what the heck's going on, and we end with them saying, oh man, we need to hear a little bit more about this, this, and this. And I'll go back and I'll make videos about it, including solving problems, showing examples of problems. And so the idea of having the students really have a say in what they're confused about, what they need more help on, is really cool.
Number 12. And so I'm going to make an effort to make a video to go through all of those three. I'm going to start with number 9. And I will also be posting the answer key to number 10 later on in the week. If there's any other problem that comes before number 9 you were really stuck on, you really need help with, please do try to see me during office hours or during class this week after we've discussed and dismissed. Okay? All right, so first off, number 9 asks about a child in a wagon. Whoa.
I hate when that happens.
So here's our wagon. Here's our little person.
Awesome.
And he's
great.
sitting there while he's being pushed.
I think that's Microsoft Word doing that.
And when it comes down to
that's
it,
too bad.
The pushes are the thing that we really care about. So we've got one child pushing on the wagon in one direction with a force of, let's call this guy 45 newtons. And then the child number 2 is pushing opposite of child number 1 with a force of 90 newtons.
So it's really interesting to label these things as C1 and C2 as opposed to F1 or F2. I think that when you do a massive force free body diagram, if you label everything an F, then you have to squint at the subscripts, right? So here we still have subscripts, but we know, oh, those are the child forces, and my guess is we might have some gravity in here or something. We're certainly going to have a frictional force. So I think that those labels are interesting, and I think that you have to think about how they can see on the screen, and if you're doing this on the chalkboard, can they see the subscripts? Who was I giving some feedback to? Oh yeah, I visited a colleague, their class. It was an online class, and they had used I guess PowerPoint slides and beautiful LaTeX equations. It was really, really great. But I was telling him, I said, boy, even on my screen, going full screen, I couldn't see the subscripts that well. So it's really interesting to think about sort of that typography, those issues. So here, again, video benefits us by her being able to say C1 is the force of the child, right? She said it, but the label is going to be C. So I think that it's, to me it's quite clear, and especially with the units next to it, it sort of makes sense what's happening. The Microsoft Word jumping around stuff that she's experiencing, I hate that. I hate it. And it's not just Microsoft Word. I hate it when the software decides that my pen is somewhere else. And so sometimes what I've done is I've sort of gone to software that literally only lets you draw. You can't put in text, you can't put in anything, but at least it sits still, right? So you can tell that she's frustrated about it, and you can tell that she's able to keep going with her train of thought about what it is she wants her students to learn, even while she's dealing with that frustration. I think that's actually really cool.
Then we have a friction force, which would oppose motion. We're going to talk about where to put that on this diagram. of 12 newtons. Mass of the third child plus the wagon is 23 kilograms. So we were given mass. And it says, in this first one, it says, what is the system of interest of this particular, if the acceleration is the thing that we're going to calculate? And the answer is the child plus the wagon.
Yeah, and that's given away up here when you can see how the mass was
The
given.
second says to draw a free body diagram including all forces acting on the system. So again, when we do that, we draw a point. We draw forces that are acting on the system. Weight and normal are always in the diagram. We've got one child pushing to the right. So that's child one's force of 45 newtons. We've got child two's force, which is going to be bigger, 90 newtons. Since this child is...
So this is great. Love it. And she's going to have to add friction here in a second. The thing that I wanted to sort of call your attention to is the technology. So when she's writing, there's a little blue dot, and of course you can see the black ink that she's leaving behind. And when she's not writing, there's this super awesome yellow circle around her cursor that really catches the eye. And I think that's actually whatever screen recording software she's using, whatever this little icon is. It's interesting that as she's writing quick little strokes, it's a little bit hard to see what's going on, but boy, it's beautifully clean when it's all done. And there's no question what part of the screen she wants you looking at, both with the yellow circle and then the blue dot and then the black trail it leaves behind. You know, I was thinking about this problem. I was trying to think about the frictional direction. Is it possible the frictional direction is ambiguous here? So normally we'd say, oh, well, this child's winning, so it's moving to the left, so the frictional force is going to be to the right. My guess is that's where she's going here. But it's funny, I just had a conversation on Twitter yesterday about this, like, what direction is the frictional force? Does it always have to be, you know, fighting against the velocity? Could it be fighting against the acceleration you're feeling? Because imagine if this wagon was already cruising along really, really fast. Sliding, you know, she drew it with wheels, and so rolling friction is a whole other thing. I guess I'd rather think about this as a sliding thing. Imagine it was moving to the right super fast. It may be that this problem says it's at rest, and if that's the case, then easy. But if it's cruising along to the right, then really child 2 is trying to slow it down. Child 1 is saying, hey, come on, let's go faster. And the frictional force would actually be to the left. So directions for frictional force are super hard. They rack your brain. And, you know, maybe I'll post a link to the Twitter conversation I was having yesterday. It took me a while to wrap my brain around it as well. So I'm just going to go back here. So 306 is where we are now. I'm just going to go back far enough that we can read the problem again. It does not say that it starts at rest. So I'm just going to make some predictions here. I think she's going to say it was at rest and cruise. But there's also sort of the real life, how could this possibly work? If this thing was zipping along to the right, it would be hard for this person. They'd have to be running backwards and trying to slow it down. That's actually difficult to do. I think that we're supposed to assume this starts at rest. And again, she's got these interesting wheels. I'm curious if she's going to address that, because the wheels are a whole other thing. You know, rolling friction is super complicated and, in fact, quite minimal. Right? That's why we're able to push these strong these performers, right, who can grab things and pull planes and push trucks and stuff like that. It's because there's hardly any friction. So anyways, let me get myself back to 306. Oops. How about here? There we go.
Moving with double the force, it means the wagon itself will actually move to the left. So that means we're going to double the force, which is going to be bigger. 90 newtons. Since this child is moving with double the force, it means the wagon itself will actually move to the left. So that means we're going to put friction pointing opposite of the movement.
So she did it really fast. She said, "Oh well, they're fighting, and this child two is pushing twice as hard, so it's definitely winning, right?" So there's this implicit notion that it's starting at rest, but I think that the way she drew it, the way she presented it, I would be astounded if students sort of missed that, right, and started making these crazy arguments like I was making. Oh wait, what if it was moving already? So, and also think about the scaffolding, right? Very, very, very likely they haven't dealt with complex situations yet. So, now she's got her beautiful drawing, and in fact, you can already tell that because this is less than 45, child two is still winning. Well, and actually, I guess it has to be right because she made the decision about the frictional force direction. And then, of course, all we have to do is calculate the acceleration. So now it's just some quick arithmetic. I'm curious to see if she just immediately says they're fighting against each other and adds these up and subtracts it from this, or if she does some sort of algebraic system where she calls, I don't know, how about left negative and right positive? That's a really interesting approach too. Let's see how she does it.
Okay. And so when it comes down to it, you need to make sure you're understanding what's happening in this particular system before you can draw a free body diagram. And it did tell you that friction opposes motion. The big takeaway here is whatever the net force is the direction of motion.
Yeah.
And it's going to be the thing with the largest force.
So, okay. So that absolutely makes sense in the context of this problem, no question about it. It's not always true, though, right? Because if it was already moving and you're slowing down, your net force is not in the direction of motion. So, man, this is complicated, right? And so she's for sure going to be doing some, sorry if you hate this word, deceleration problems soon in this class. You know it. And so here she's trying to give them some scaffolding of how to do these kind of problems. And there's going to do a ton of them, and you really have to think about it because friction is tricky. And that statement that the net force determines the direction of motion, really the only thing that we need to change in that sentence to make it universally true is to put a little word right here, the direction of, or three words, the change of motion, right? Because force changes the motion somehow, can change the direction, can change the amount of motion. Boy, this is really, really interesting. And what I'd love, and I'm probably not going to follow along enough to know, but it would be really curious to see if she, starts to do deceleration problems and say, okay, well, in this one, the force is not in the direction of motion. And so, whereas what she's doing now is absolutely going to enable them to work these problems well. And it's a really, really great way to think about it. These static problems where most of the time things are sort of sitting still and you're wondering, okay, if these forces get applied, which way will it move? Absolutely 100% this statement is super, super useful for that. But then, so you've built this really, really strong tool, scaffold that your students can use. Then you run into other situations later on, next day, the next week, right? You can just give them a new set of tools and say, oh, hey, if you're dealing with a problem like this, use these set of tools. Dealing with a problem like this, use these set of tools. That can work. But do you also go back and say, oh, hey, remember that tool that I told you about? We're actually just going to add a couple of adjectives in here because now there's some really interesting, subtle things going on. I'm really intrigued by that as you slowly build these tools for students and to help them think, okay, yeah, well, you're right. I guess we did think about it that way last time, and now we're thinking about it this way. I keep coming back to the example of how relativity screws up momentum, screws up kinetic energy. So in relativity, you show, okay, let's smash two things together and show that momentum is conserved. Ooh, let's look at that from a passerby who's walking by as they observe it, and carefully do all of our relativistic transformations. And oh, crap! Mass times velocity, the sum of mass times velocity doesn't get conserved. And it's interesting because what I say to my students is, well, let's find something else that is conserved. And it turns out that if you do gamma mv, who knew, right? Gamma mv. Oh, well, that's something that gets conserved. Let's call that momentum, right? And my students hate it. And we have this really interesting conversation about they spent a year being told lies. And then, we take a look at gamma and we say, well, come on, let's talk about everyday experiences. What happens if your speeds are way less than the speed of light? And this thing really does approximate to being MV. So we have to sort of rebuild, reinforce some old stuff that has gotten stuck in a rut. So anyways, I think this is really, really interesting. Let's keep going.
So in our case, to the left is going to be the motion, which means friction has to go the other direction.
Yeah,
okay.
Cool.
Next thing that we're going to do is calculate the acceleration. Remember that weight equals mass times gravity if we need it. Normal opposes weight in this particular case. Don't think that really matters. But we do want to find F equals ma.
Yeah.
In order to do this particular problem, we need to calculate F net. We know that 90 is going the opposite direction. So 90 gets a negative sign.
Aha. So
Then we're going to add.
Right. She's made this choice, which I'm guessing she makes all the time in her classes, that left is negative. Left is negative. It's so weird to not be mirrored. And so therefore right has to be positive. And, some students I think really struggle with this because, the thing's obviously moving left. Let's call that positive. And I think that I've run into students who have sort of this emotional attachment to the negative sign. Like, oh, that means bad. That means wrong way. That means things aren't working. And here she's going to get a negative answer. Big deal, right? Just means, it's just our shorthand way of saying to the left. To the left. And so if you were to say to a student, you draw this, you say, hey guys, who wins? And they say, oh, obviously this wins, right? They're done. They've actually done the arithmetic in their head. Here we're trying to just be clear about it. And of course, this approach can really help you when it gets complicated. Like, hey, help yourself. Arbitrarily define one direction as positive, the other one will be negative, and then you can carefully lay them all out. Absolutely. And yet they can sometimes, get befuddled with our calculator and get an answer that just doesn't make any sense. Or they'll say, oh, I got a negative number. Shoot, I screwed up. And what I do is say, oh, well, okay, what does negative mean there? Oh, it means bad. It doesn't mean bad, right? It means, we have determined that negative means it's just shorthand for left. In fact, that's another way to do it is you could just say left. Well, no, because then you have to clearly show that left and right fight against each other. But I don't know. I'm always intrigued by these sort of setups, these algebraic setups, how to help students with their calculator on the one hand and recognize their sort of gut instinct on the other hand when they're looking at the drawing.
Add the two forces that are pointing to the right to get our net force is equal to, hold please, gotta get me a calculator.
What is that, 33? Sorry, negative 33?
Negative 33 newtons. From there, we're going to use that negative 33 newtons, set it equal to the 23 kilograms times the A we don't know.
Yeah. So a tenth of a G, an eighth of a G, something like that. No, a little bit more than that. Yeah.
And we're going to get a negative 1.
You'd feel it, for sure.
43 meters per second squared as the acceleration.
So how do I do some gut checks on this? Okay, so I'm going to call that 1.5. That means that in 4 seconds, I'm going to be going 6 meters per second. And 6 meters per second is about, 15 miles an hour. So in 4 seconds to go 15 miles an hour, 1,001, 1,002, 1,003, 1,004. Like, think about like accelerating from a stop sign in a neighborhood where the speed limit is, really, like around a school, 15, 20 miles an hour. Taking 4 seconds to get up to that speed, you don't really feel like you're jammed against the seat, so we're not going to kill this kid.
Okay. The next problem asks, what happens if friction is 15? So instead, our F net
So I'm smiling here because there's a subtlety to this part D, right? Which she has written absolutely right. It's going to work fine. It's going to turn out being 30, right? Negative 30 newtons. But what if it had said the acceleration of friction was 50? right? 50 newtons. Well, then she would do minus 90 plus 45 plus 50. But the 50 should go the other way. Wow, that is a tricky problem. But with 15, she's safe, right? 15, she's safe. I'm curious, how she wraps this up.
Becomes negative 30. And we know that F net equals MA. So negative 30 equals the 23 kilograms still, because it doesn't say the system changes its mass or anything.
Oh, I like that. It doesn't say the system changed. That's cool.
And this time the acceleration gets slower. You get that.
Okay, so awesome work, but I'm kind of fixated on what happened if D had said 50 newtons. If D had said 50 newtons for friction, would we still say it's acting to the right? No, we can't. My brain hurts. Okay, so let's go back to her free body diagram, somewhere in this vicinity. If it had been 90, 45, and 50, well, the 45 and 50 would have been greater than 90, so the thing would have been moving to the right, but then the frictional force would not have been against the motion. So you say, oh, well, then 50 goes the other way. Then you've got 90 plus 50, and you can't win. Wow! You can't just pick any old number for this. Oh, my brain hurts. You can't just stick any old number you want in here. So thank goodness she chose 15, because if she had chose anything above 45, this problem would be hard to do using this setup. Wow, that's so cool. All right, you guys, give me your thoughts about that. Maybe my brain has just frozen and I'm not thinking clearly here, but I find that fascinating. What I really liked about this video was the interesting choice of the names of the forces, right? It's like, hey, that's a child, so you're not forgetting who's who. I think that really fixating on what direction the frictional force was the frictional force was going in was really, really fascinating. And then she said, oh, remember, the net force always determines the direction of motion. And then that's certainly true in these start from rest problems, but what if you're not starting from rest? So there's some real subtleties to this. And it sort of points out to us, wow, we have to be careful what we serve our students, because if we serve them the entire smorgasbord, it gets confusing. So we carefully and slowly build them the tools to be successful. I really like that. So thanks, everybody. Have a great day. And remember, physics teachers are awesome.